And that equation is very essential for you to know. Now, if you take that derivative of this, it is the derivative of v is simply dv dt and r times d omega dt, taking the derivative of this part. You get dv acceleration equals radius alpha, and alpha is the rotational analog of acceleration. So this is angular acceleration. And this is also a formula you need to memorize because you should know that dv dt is simply equal to acceleration. And the derivative of omega is just acceleration because they're just like analogs of each other, so it should be simple. So angular velocity is defined as the rate of change of angular displacement. So you should memorize that omega equals angular displacement over delta t. And omega simply is equal to the derivative of angular displacement, just like v equals the displacement over time. Since they're just rotational analogs, this should be really simple for you to memorize. And then angular acceleration is equal to the angular velocity over time. That is also very essential for you to memorize. And same thing, angular acceleration is equal to the derivative of angular velocity, just like a is equal to dv dt. Same thing. And what's also simple for you to memorize is 1 revolution is equal to 2 pi radians, which is equal to 360 degrees. So just in a circle, 1 revolution. You get that, yeah. Simple math. Okay. So another formula you need to memorize is omega squared times r, which is equal to centripetal acceleration. So you should know that centripetal acceleration is equal to v squared over r, and to make it rotational kinematics, we talked about how v is equal to radius times the angular velocity, so you just plug that in for v, and then that's how you get this equation. And the last thing you need to know is the big five for rotational kinematics, which should be simple because just think of the rotational analogs of each other, like angular velocity, v, the initial angular velocity, initial velocity. And you just go from there, But these two are the main ones you need to, you use for rotational kinematics. So if you just want to, memorize those, just memorize it. But it's you just need rotational analogs, like I said. We're not going to do an example problem for this topic because you just need to know the formulas and just apply it. Simple. So for the harder problems, you have to think about it, but it's just basically the formulas. So also for rotational dynamics, what you need to know about that is the dynamics of translational motion involving describing the acceleration of an object in terms of its mass, inertia, and the forces that act on it. F net equals ma. By analogy, the dynamics of rotational motion involve describing the angular rotational acceleration of an object in terms of its rotational inertia and the torques that act on it. So that's what rotational dynamics is. Now for the last topic you need to know, angular momentum and its conservation. So angular momentum is a rotational analog for just linear momentum. So again, it's pretty simple, just like the last topic. So consider a small point m at distance r from the axis of rotation, moving with velocity v and acted upon by a gentle force F. So this is like the conceptual stuff of it. So just memorize the force goes up, velocity goes up. Okay. So a very important equation you need to memorize is angular momentum. So it's L. Angular momentum is denoted by L. It's equal to inertia times angular velocity, or omega. So by Newton's second law, you should know that the force is equal to delta P over delta T, and delta P is just momentum in its linear manner. And you should know that P is equal to mass times velocity. So that's how you get delta mass times velocity over delta T. And the torque, so if you multiply both sides of the equation by R, you should notice that you get radius times force is equal to the torque. So you'll get torque is equal to delta RmV divided by delta T. So now we say that the torque is equal to the rate of change of angular momentum, and the angular momentum denoted by L of the point mass m is defined by the equation angular momentum equals to RmV. And mass time radius is just inertia, and the velocity, the rotational analog, is omega, So that's how you get this equation. That's just how you form this. So in case you're wondering, you don't need to know, but know for the AP Physics exam, it's not like they're going to ask you, how do you form this equation? But anyways, if the point mass m does not move in a circular path, we can still define its angular momentum relative to any reference point. So here's a little diagram I made. So if r is the vector from the reference point to the mass, then the angular momentum is momentum equals radius times mass times velocity perpendicular. Then you set that equal to radius times the momentum that is perpendicular. And then you get angular momentum is equal to radius times momentum, which is equal to inertia times angular velocity, or omega. It's okay if you don't get the conceptual stuff of physics right away. Once you get used to it for a couple of times and you think about it logically, then you're like, oh, okay. But for now, what you should get really out of this is memorizing the formulas and how to use the formulas, because that will really help in physics. So, but once you do more problems like that, you'll start to see the conceptual side of stuff, and then you'll get into more problems. So yeah, let's just get back to this. So here's an example. So a solid uniform sphere of mass m is equal to 8 kilograms and radius r is 50 centimeters, is revolving around an axis through its center at an angular speed of 10 radians per second. Given that the rotational inertia of the sphere is equal to 2/5 mr squared, they'll always give you the inertia formula, unless it's just the regular inertia. If it has a shape, so in this case it's a sphere, they'll give you the formula. You don't need to memorize those, but you do need to know that inertia is simply mass times radius. But yeah, moving on. What is the spinning sphere's angular momentum? So it's asking for angular momentum, so you just need to know the equation. Angular momentum is equal to inertia times the angular speed. So they give you the formula for inertia, so you plug that in times omega, and then you know your mass, you know your radius, and you know the angular speed, so you just plug in the numerical values, and then you get 8. And these are the units for angular momentum, so you should memorize that too. And yeah. Now for the very last thing that you need to know is its conservation. You just need to know that F net is equal to the derivative of momentum, so dB dt, F naught is equal to 0 and P is constant. Now torque is equal to the derivative of angular momentum, and if there's no external torque acted on the system, the torque is equal to 0, or dL dt is equal to 0. Now integrating this equation, we get L as constant, or inertia and angular velocity constant. So this is the principle of conservation of angular momentum. You just need to memorize that. There's no example problem. And because I just want you to memorize this for now. We aren't going to go through this example problem, but if you're just interested to know, one of you like studious people who are watching this video, you could go through it. If you get it, great. I'm pretty sure you're smart. So here's just a little look through. But one thing to note about this problem is that usually it's conservation's problem. It has like something to do with the skater, and it's like arm is like going in and then they're going out with their legs. So yeah. So this is just like this particular problem. And for this problem, it's very helpful to draw a picture. So you should generally draw a picture. So yeah. And then we are done bibliography. Yeah, I hope you enjoyed this video, and I hope you understand the topics that we discussed, and I wish you very good luck in AP Physics next year.